In this problem, we have a potential energy for a one-dimensional mass at a distance r from an origin being given as u of r is u naught times the quantity small r over capital R plus c squared capital R over r, and that's lowercase r on the bottom, for lowercase r going from 0 to infinity, where capital R, C, and U naught are all positive constants. And for part A of this problem, we want to find the equilibrium position, which we're told to label as R naught. So the key to doing the first part of this problem is to understand that the equilibrium position is always going to be equal to when the force is 0. So when the forces on your system balance out, then you're in equilibrium. We know then also that if we have a potential U, we can find the force by taking the -1 times the gradient of that potential. And since this is a symmetric potential around R, this is going to end up just being negative the derivative of U with respect to R. So if we evaluate that, we get that our force is equal to U naught times the derivative of this is just 1 over r, and there's going to be a negative here, plus c squared r, and then this r to the negative first power becomes an r to the negative second, and it drops a -1 here. So something like this, and then we know that for equilibrium, our force is 0, and this is going to specifically be when we have r is equal to r naught. And so then we can distribute this u naught here. And so we have negative u naught over r plus u naught c squared r over r naught squared equals 0. Shuffle this negative u naught over r to the other side by adding it. And so then we have u naught c squared r over r naught squared equals u naught over r. And then we can swap r naught squared with u naught over r. And so if we do that, we're left with r naught squared equals u naught c squared r squared. And so then over u naught. And so we can cancel out the two u naughts and then take the square root of both sides. And we just get that the equilibrium position R naught is just CR. And that's our answer to part A here. Next, we want to show that if x is the distance from equilibrium, that for a small x, where x is much, much less than 1, the potential energy can be expressed as U is equal to a constant plus 1/2 kx squared. So the way that we usually get estimates for these sorts of things is to write it out as a Taylor series. And here we're going to choose a Taylor series of U centered around our equilibrium position R naught. And we can write it out like this. We then know that since x is just how far we are from our equilibrium position, it can be written as r minus r naught. Our actual position in space minus our equilibrium position is going to be our displacement from the equilibrium position. If we look at this, we actually see that we have an x to the power of n in this Taylor series then. And so for successively larger n's, you're going to be raising x to successively larger powers. And since x is significantly less than 1, the higher you go in n, the smaller your term is going to be. And so for this reason, we can sort of pick the first non-constant term that we get, and that will give us a pretty fair estimate of our potential. So if we pick the first term, n equals 0, we have u to the 0th derivative, which is just u of r naught, over 0 factorial, which is just 1. And then this is going to be times all this stuff to the 0th power, which just makes it a 1. And so we actually don't care about the 0th term here because it's just a constant. So we can ignore that. Then if we look at the second term, it's going to be n equals 1. So u, the first derivative of u with respect to r naught over 1 factorial is 1 again, and then r minus r naught to the first power. But then if we look at this, we know that u prime of r naught is going to be equal to 0 because u prime of r naught is just equal to the negative force of r naught. But the force of r naught is equal to 0 because that's our equilibrium position. That's specifically what we solved for earlier. So this term is just 0. So we could ignore it. And then our third term is going to be u double prime of r naught over n factorial, which in this case will be 2, since it's 2 factorial, times r minus r naught squared. So we can then rewrite r minus r naught as x. So we have an x squared term here. We have a 1/2 from this here. And then for u double prime, we already found u prime to be equal to u naught times the quantity 1 over r minus c squared r over r squared. And if we take the derivative of this again with respect to r, then we end up getting u double prime of r. This is a constant, so it drops out, and you get another negative 2 up here. So 2, the negatives cancel. U naught, we'll just multiply that in, c squared r, and then we drop another place for our exponent there. So r cubed. We can then plug in specifically r naught. So this is u double prime of r naught, which is just 2 u naught c squared r over, and then r naught was just cr, so over c cubed r cubed. And so then we cancel out all the c's on top, and we're left with the c on the bottom, and one of our r's up here, and we're left with an r squared term down here. So u double prime of r naught is just equal to 2 u naught over c r squared. And if we now plug this into our expression here, we can write this as 1/2 times the quantity 2 u naught over c r squared times x squared. And so then our k value, our constant, is just going to be equal to this piece. So k equals 2 u naught over c r squared. And that's part B. Part C, then, we want to figure out the angular velocity of this motion. So we know that for a spring, the angular velocity is just the square root of the spring constant k over the mass. And since we already found the spring constant to be k is 2 u naught over cr squared, we can just plug that into this expression. And so our angular velocity is just square root 2 u naught over cmr squared. And that's how you solve this problem.